So thank you for joining this lesson. Today we'll be discussing physics paper 2, just as I had promised you. I can see you are already in. I'm waiting for my teacher to do it. I'm here. Thank you. Thank you so much. So now allow me bring the paper 2 that we are going to discuss. Okay, so this is one of the serious exams which have been done in this season. Remember, our consultation line is 0704 153 366. Number one, a ray is incident on two mirrors inclined at 60 degrees as shown in the diagram below. So for 3 marks, we are taught to determine the angle of reflection on mirror A, and also, or else, we trace the path of the ray as it leaves mirror B. So we should know that whatever has been indicated here is not the angle of reflection, neither is it the angle of incidence. You should be able to define those angles. So at the point of incidence, if we draw a normal at that point, then now we will say that the angle between the normal and the ray is the one called the angle of incidence. And now that we have an angle out there, which is 40, and the normal is usually perpendicular, then the angle is exactly here, 50 degrees. So the angle of incidence is 50 degrees. Now that the ray has to be reflected following the laws of reflection, then it has to leave the mirror, making an angle of reflection which is equal to the angle of incidence, and that is exactly 50 degrees. So the angle of reflection now is also 50 degrees. Remember, there must be an arrow for the ray. That's an arrow. Remember, if this is 50, then we automatically have a 40 degrees angle here. And now we can see now the ray is incident again to mirror B. If it's incident to mirror B, then it means now we need to say that there is 40 degrees angle, 60 degrees angle at this point. That is 100. So the angle here is going to be 80 degrees. So the angle there is of 80 degrees. And now we can draw again a normal at the point of incidence with mirror B. So if this is a normal, then now we will have an angle of incidence, which is 10. So the angle here is going to be 10 degrees. So that it leaves that mirror through an angle of reflection also of 10. So we shall have an angle. Now the ray goes out now, leaving 80 at this point and at 10 at that point. So now we are having the ray sketched until it leaves mirror B. So that is how it happens. Let's look at number 2. The question says that the coils P and S are connected as shown below. P is connected to a battery, then a rheostat, and a switch K, just as you can see the diagram. S is connected to a galvanometer, again, as you can see. State the behavior of the pointer on G, that is galvanometer G, in the following cases. 1, when K is switched on, that is when the switch is closed. So when you close the switch, we are going to see a deflection in one direction, then back to 0. The galvanometer deflects in one direction, then back to zero, then back to zero. That is the observation. A student is supposed to know that the point that it reflects or it deflects back to zero is very important, and it's part of the observation. So you cannot say that the galvanometer deflects in a certain direction and you leave it at that point. You must include that it comes back to zero, because once you close the switch, we expect current to build up from zero to maximum, hence inducing magnetism in the primary coil. And so the magnet in the primary coil is going to be saturated once the current is maximum. And so there will be no more magnetic flux linkage to the secondary. And if there will be no more magnetic flux linkage, then we will not expect any current to be induced in the secondary coil. And so the deflection has to fall back to zero, or rather the pointer of the galvanometer has to fall back to zero. When K is opened, remember there is a direction that you've mentioned in Roman 1. So when the K is opened, we say that the galvanometer or the pointer in the galvanometer deflects in the opposite direction. That is opposite to what we have there. In the opposite direction, then back to zero. Then back to zero. Opposite direction to the direction which it had deflected in Roman 1. So it has to deflect in the opposite direction and back to zero. It has also to be noted that the opposite deflection now is always greater than the deflection in the first case when there is the switching on. Greater because the magnetic flux linkage is greater because of the rate of magnetic flux linkage, which is now greater due to the dying off of magnetism, which takes relatively shorter time than the building up of magnetism. So because a magnet, or because current takes shorter time to die from maximum to zero than it takes to build up from zero to maximum, then we expect the rate of magnetic flux linkage to be greater during the switching off than the switching on. I believe you are still following. I believe you are still following us. Let me check what is happening around. Yeah, this is good. Remember to like, remember to subscribe, remember to invite a friend to this lesson so that we may learn together. So thank you so much for the continued support. All right. Part B, a transformer has 200 turns in the primary coil and 1,000 turns in the secondary coil. If the transformer is 100% efficient and the current in the secondary coil is 0.15 amperes, determine the current in the primary coil. So what we are supposed to know is that there is what we call the transformer equation. Whereby the number of turns in the secondary divided by the number of turns in the primary, this one is called the turns ratio, is usually equal to the voltage in the secondary out of the voltage in the primary. And this is the same as current in the primary. Now we overturn for current equals to current in the secondary. Primary over secondary for the current. This is because for an ideal transformer, we expect 100% efficiency, whereby power input and power output is usually equal And so when you consider the last part of the equation, then you will discover that for an ideal transformer, if you cross multiply, you shall have voltage in the primary times current in the primary. That gives power input. When you cross multiply the other side, voltage secondary and current secondary, that is power output. So we'll say that they will be equal for an ideal case of a transformer. And so we need to know that this is now the transformer equations. So now we can equate directly the number of turns and the current, whereby we say number of turns in the secondary, which is 1,000, divided by number of turns in the primary, which is 200. This is the same as current in the secondary divided by current in primary. Okay, current in primary is unknown. Out of current in the secondary indicated as 0.15. So we can now get current in the primary by cross multiplying 1,000 times 0.15 divided by 200. This is going to be 0.75 amperes. So that is the current in the primary coil. Number 3, the question says that the figure below shows a simple experiment using a permanent magnet and two metal bars, A and B. Put close to ion filings. So metals A and B are put close to ion filings. Then somebody tells us that now they have been taken away. The permanent magnet is now removed from them, and we have the two now after the experiment. We have some ion filings which have been attached to them. State with a reason which bar is made from a soft magnetic material. This is a question which requires a student to seriously reason and come up with a conclusion. Remember, they are not connected to the permanent magnet now. And therefore, we can see, okay, what we are experimenting is how fast can they lose magnetism. When you look at B, it has very few ion filings, which means it is losing its magnetism very fast. But A is still holding a bigger number of ion filings. So it means that B is a soft magnetic material because it seems to have lost magnetism very fast. B is the soft magnetic material. This is because it is losing the magnetism. It's losing its magnetism. It's losing its magnetism faster than A. There is evidence that it is losing magnetism, and there is evidence that A is still holding on. Check this alternative question. If we had been asked the same, but still having the permanent magnet in place, if we had the permanent magnet in place, then we would have said that A is a soft magnetic material because we can see during magnetism, it's gaining magnetism very fast. But now that they have been taken aside, then this is to experiment which one is losing magnetism faster. Remember, soft magnetic materials will gain magnetism very fast and lose the same magnetism also very fast. Another question in number 4. The diagram below shows a ray of light XY traveling through a glass block of critical angle 42 degrees to point A. As you can see, the ray of light XY traveling to a block here at point A. calculate the refractive index of the glass block. The first thing is to calculate the refractive index of the glass block. Remember, refractive index is usually given by 1 out of the sine of C, whereby C is the critical angle. So refractive index will be given by 1 out of the sine of 42 degrees. According to the instructions there, we've been told that the glass block is having a critical angle of 42. So 1 divided by the sine of 42, this is exactly 1.49. 1.49. Refractive index is a ratio, and so we don't expect SI units for that. Just be aware of that. There is more questions on part B. On the same diagram, draw the path of the ray as it travels past point A. I must mention something about a critical angle. Critical angle is the angle of incidence in the denser medium for which the angle of refraction in the less dense medium is 90 degrees. That means if the angle of incidence is increased beyond the critical angle, then total internal reflection occurs in the denser medium now. So we can look at the angle of incidence in our case, whereby if this is 43, then we shall have 47 at this point. You can see our normal is well drawn. This means now the angle of incidence of 47 is greater than the critical angle of 42, and hence the ray will not go into the other medium, but total internal reflection shall occur. And so we expect the ray to be reflected internally now within the same medium, within the same glass block. We expect the ray to be inside here. So the ray is going to be reflected obeying all the laws of reflection, such that this is also 47, leaving a 43 at this point. So that is how the ray behaves. Thank you so much. I can see you are still turning up. Continue quoting your school and your math, your physics teacher tonight. Sorry. Today we are greeting our physics teachers. Say hi to Mwalimu Afik. Please greet your physics teacher. Greet your physics teacher tonight. Greet your physics teacher. Remember to invite a friend. Remember to invite a friend. Remember also to subscribe to this channel. You must be subscribed to your best mathematics and physics platform. Please be subscribed to our channel. Please be subscribed. We are continuing with the paper. I'm setting up a few things here. Please remain subscribed. Remain a serious sharer of our live broadcasts. You can see people, from serious schools. Wow, thank you so much. Mr. Felix, Machako School. These are colleagues of mine. Wonderful. I will say hi to them. This is great. This is great. This is great. This is great. Say hi to your physics teacher tonight. Tomorrow during mathematics, we will be greeting our principals. We will be greeting our principals. This is wonderful. This is really wonderful. This is really wonderful. Now we can continue. We can continue. The photoelectrons liberated from an illuminated, illuminated metal surface constitute a photoelectric current. Very true. what is the effect of decreasing the intensity of the illumination on the magnitude of the photoelectric current? So the photoelectric current, which is produced during photoemission or photoelectric effect, is usually directly proportional to the intensity of the radiation which is causing the illumination. And so if we decrease the intensity of the illumination, it means the rate, or okay, the photoemission will be decreased. And so photoelectric current that will flow will be little. So we are saying that the photoelectric current, the photoelectric current decreases. The photoelectric current decreases because definitely the rate of photoelectric effect also decreases. Let's look at this question number 6 now. We are told that the figure below shows a battery of EMF 3.0 volts connected in series with two capacitors. So we got two capacitors here connected in series, and they are also in series to the 3.0 volts battery. Determine the energy stored in the combined capacitors when the switch is closed. So when you close the switch, charge is going to flow and energy will be done, or rather there will be work done during the movement of the charges across the potential differences in the given capacitors. So what we can do first is to calculate the effective capacitance, and you can see that the capacitors are in series to one another. So we usually say that capacitance, when in series, the total capacitance is usually given by 1 out of the first capacitance plus 1 over the second one plus, so the addition can continue until we add the reciprocal of the last one. In our case, let us talk about two cases only, whereby we will say capacitance total for only two cases which are in series can be given by the product of the capacitors divided by the sum of the capacitors. So what do we need in this case? We need 3 times 3 divided by 3 plus 3, which is 6. So 3 plus 3. 3 plus 3. This will be 9 over 6. 9 divided by 6. This is giving me 1.5 microfarads. 1.5 microfarads. 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 1.5 microfarads. This one is the effective capacitance. Instead of microfarads, we can also have 1.5. We multiply by 10 power negative 6, so that the capacitance is in farads. Times 10 power negative 6 is another way of dividing by a million to get the SI units. Thank you so much. I can see you guys are really chatting. Thank you, thank you, thank you, thank you. All right, I sent greetings to Madam Rob Faith. When you go back to school, kindly tell your teachers to get their greetings from this platform. We are sending greetings and love to our physics teachers tonight. All right, it's good for students to know that there is something called charge. Charge is abbreviated Q, and Q is usually given by CV. Capacitance multiplied by voltage. So capacitance is 1.5 and V is exactly 3. So what we get when we multiply by 3 is 4.5. 4.5 times 10 power negative 6. This is charge. Now we will talk about coulombs. This being charge, we shall talk about coulombs. This one will be understood by the candidates who are following us. If you know a candidate somewhere who is not serious with studies, please invite them to this platform. They will get transformed. They are going to learn something. All right. Moigal's ed rate. Wow, this is international. Think we are doing great. This is wonderful. Mr. Savai Ngoto Boys. Wow, this is wonderful. I can see George from Ngoto Boys sending greetings to Mr. Savai, my colleague. This is great. So after we've gotten our charge, now we will tell ourselves that the energy is usually given by half Q times V. Half Q times V. This formula can be manipulated to several other forms because we can change Q using the first equation there. We can also change V using the same equation. And so what we need to do is just take half, we substitute Q, which is 4.5 times 10 power negative 6. Then we multiply this by V, which is equal to, the V is 3. We multiply now by 3. So I can multiply this by 3 and also by a half. I'm getting 6.75. 6.75 times 10 power negative 6. Because it is energy, now we shall talk about joules. Energy in joules. Energy in joules. Energy in joules. Okay. I'll be sending greetings to your teachers after every minute. After every question, I'll be confirming the new teachers that you are saying hi to. Remember to invite a friend. Please remember to invite a friend. Join us for a powerful physics lesson. I can see people saying that they have understood, and this is wonderful. This is wonderful. Welcome and continue learning with us. All right. Can see people from Zimbabwe. Wow, this is great. This is great. Let's look at this question. Please make sure you are attentive. Make sure you are attentive. The figure below shows a meter rule in equilibrium with a magnet and weight W. The soft iron core is fixed to the bench. So we have a soft iron core fixed to a bench. As you can see, we have the bench top there. There is a circuit there connected to the soft iron core. We have a magnet. Then there is a meter rule there, whereby the weight of the meter rule is acting downward through the center, of course. Then it has been supported or hung using a string somewhere. It has been pivoted up there. State and explain the effect on the meter rule when the switch is closed. So when we close switch S, one thing we are sure is that current is going to flow. And because there is a soft iron core, being a soft magnetic material, it will get magnetized very easily. It will get magnetized. Once it has been magnetized now, there will be some effect to the equilibrium of the meter rule that you can see above that. Now, we are going to examine the kind of an effect that we expect. As we try to examine the kind of an effect that we expect, we will ask ourselves a few things. When the current flows, what kind of a polarity is going to be formed on the upper side? What kind of a polarity, or which polarity do we expect on the upper side of the soft iron core? That polarity is the one to help us know whether the meter rule or the magnet on the meter rule is going to be pushed up. Remember, it has a north there. whether it will be repelled upwards or attracted downwards, and that will bring the overall effect on the equilibrium or on the way it's going to turn. So can we talk about a current flowing? Then what we have here, the current will flow in such a manner that yeah, it will flow this way, this way, this way, so that it flows back now to the source. All right, we can use several rules in this case. We can use the right hand grip rule. We can also use what we call apart from the right hand grip rule, we can also use the clock rule. The clock rule, such that when I look at the current, sorry, let us look at the way the batteries have been connected. Let's look at the way the batteries have been connected. Sorry for this. You will be able to see that because the positive terminal is at this end. Sorry for that. Current will be flowing this way, then back here, such that at this point, current now has to flow in such a direction, such a direction, such a direction. So that is how current is going to be flowing around the soft iron core. So the magnet which will be caused can now be determined following the clock rule. If we choose to follow the clock rule, then we will be able to tell ourselves, if we observe it through this point, let's say we are standing there and we want to observe the flow. We want to observe the flow of current. Then from where I have put my arrow, the current will be flowing in what we call an anti-clockwise direction. It will be flowing in a, let's say in a clockwise direction, sure. So we can also hold using the right hand grip rule, whereby if you hold your finger this way, I hope you can see my finger. If you grasp the iron core this way, such that these ones, the fingers show the direction of current, as you can see, then the thumb is going to point the north. Therefore, if I hold this soft iron core, then my north is going to be at this point. That means automatically south will be on the upper side. Or because on the upper side, current is flowing in the clockwise direction, then according to the clock rule, that is going to be a south pole. And with a south pole there, we shall have this north now attracted. So we shall have an attraction, which means the meter rule is no longer going to be at equilibrium. It shall be tilted or twisted, and it will rotate in an anti-clockwise direction. State and explain the effect on the meter rule when the switch S is closed. It shall tilt or rotate. It shall rotate in the anti-clockwise direction. In the anti-clockwise direction. Let's follow up with this paper until we finish. In the anti-clockwise direction, reason being, the soft iron is magnetized. The soft iron core is magnetized. It's magnetized. It's magnetized with a south. With a south on the upper side, attracting the magnet on the meter rule or the rule, and definitely now the turning effect will appear. Now the turning effect is going to be experienced. State how polarization is reduced in a dry cell. We use a potassium dichromate, which is a depolarizer, by the use of a depolarizer. The use of a depolarizer, for example, potassium dichromate. Potassium dichromate. When you say the use of a depolarizer, it's advisable you state an example of a depolarizer. It's advisable. Remember to continue sending greetings. Nakuru, hi. This is great. Wow, this is wonderful. This is wonderful. Let's send greetings to our teachers, please. Wow, this is wonderful. This is wonderful. Wonderful, wonderful. Remember, this is our consultation line, 0704 153 366. Tomorrow we shall be doing mathematics, and we will be sending greetings to our dear principals. So tomorrow we will be tagging our school and the principal or the chief principal. State two differences between the cathode ray tube, and that is the CRT of a TV, and the cathode ray oscilloscope. Some of the major differences is that in the TV tube, deflection is caused by magnetic fields. While in the CRO, the cathode ray oscilloscope, deflection of the beam is by electric fields. Deflection is by electric fields. Another possible question from such a point, you can be asked, why is it that in the TV tube, magnetic fields are preferred to electric fields? And the reason why this happens is because the magnetic fields cause a bigger deflection. Magnetic fields cause a bigger deflection of the beam of electrons than the electric fields. We can also say that the beam in a TV, is greatly, or is deflected in a greater way. Is deflected in a greater way compared to the beam which is in the CRO. So those are some of the differences. There is another interesting question here in number 10. Distinguish between a p-type and a n-type extrinsic semiconductors. Distinguish between p-type and n-type extrinsic semiconductors. It is good for you to know, generally, the extrinsic conductors are semiconductors in which impurities have been added so that conductivity is enhanced. The impurities added are called dopers, and the process is called doping. So during doping, we can add different types of atoms to enhance conductivity. And so we shall say that in the p-type, or a p-type semiconductor is the one in which the p-type semiconductor, a p-type semiconductor or extrinsic semiconductor is the one in which is the one in which doping has been done using a trivalent atom, or in which a trivalent atom has been used for doping, while a n-type semiconductor is the one in which a pentavalent atom has been used for doping. Let me give a unique difference again. Remember, you can also say because of doping using a trivalent, remember a pure semiconductor is a group 4 element. That means it will have 4 valence electrons. So when you use a trivalent atom in the doping, you find 3 of the valence electrons are used for bonding, leaving a vacancy for 1 more. And that lack of an electron, whereby an electron is negative, the lack of a negative electron becomes a positive hole, whereby it contributes or it enhances conductivity in the p-type, making holes which are positive to be majority charge carriers in the p-type, and hence the name p-type, because in p-type majority charge carriers are positive holes. On the other side, when you use a pentavalent atom, this is the one which has 5 valence electrons, whereby 4 will be used for bonding and 1 remains vacant for conductivity. Which means in n-type semiconductors, we have electrons as the majority charge carriers. Since electrons are negatively charged, then we got this name now, n-type, due to the negative charge of majority carriers in such a semiconductor. Please remember to subscribe. Remember to invite a friend. Remember to send greetings to your favorite physics teacher. This is our number. You can consult. You can request for revision materials. You can also use the same number to appreciate the good work of Shifting Grades Online School. This is your school while at home, while at school. This is school away from school. The section 2 now. I hope you are still around and copying up. I can see we started 42 minutes ago, and we shall continue. Mr. Matheka from Makueni Girls, receive your greetings from your students. Wow, Western region, we appreciate your work, sir. God bless. I'm grateful for this. Teacher, you are making physics interesting. This is great. I'm humbled. That is my pleasure. That's my weakness. Physics is my weakness. Greetings to Mr. Savai, Ngoto Boys. Wonderful. Thank you, George, from Ngoto Boys. I'm receiving all greetings from this end. Greetings from Kanunga High School, Kiambu. Wonderful. Wow. Hey to Mr. Walela and Juma, St. Columpans High School. Wonderful. Say hi to your teachers. That is great. So we can continue now with the section 2. Continue liking. Gia Girls following. Wonderful. Molo Academy represented. This is great. Physics is becoming interesting and easy. Wow, greetings from Mutulani Secondary. Wonderful, wonderful. A school from Mombasa, I receive your greetings. Khalifa, that's your teacher. Wonderful. Greetings from Mutulani. Then Mr. Dennis from Bishop Njenga Sek from Tabeta. Mr. Juma Lugulu. Wonderful. So let's now continue with the section 2. We can be faster, but ensuring that you people get everything. What is happening here? Okay, students set up a mass attached to a spring such that when it oscillates, it taps on water surface in a wide, shallow tank in figure 11 below. So we got a figure here whereby we can see a spring such that when it swings, the mass is able to splash the water. The students measured time for 20 oscillations and found that the mass takes 36 seconds. And found that the mass takes 36 seconds. Determine the periodic time. The periodic time of the mass. Then again, we determine the frequency of the waves produced on the water surface. So if a student is measuring time for 20 oscillation and they discover that for 20 oscillation, the time taken is 36 seconds, then we should know that periodic time is usually the time taken for one oscillation. So we will say 36 oscillations, 20 oscillations, 20 cycles, let me call them this, 20 cycles or 20 wavelengths are taking 36 seconds. What about just one oscillation? What about one oscillation? Shall be 36 over 20. 36 over 20 is 1.8, yeah. 36 over 20, 1.8 seconds. So the periodic time is 1.8 seconds. Time for one oscillation. Time for one oscillation. Number 2, the frequency of the waves produced on the water surface. It's good for you to know that when we talk about frequency now, it should be the reciprocal of periodic time t. So the reciprocal of 1.8, the reciprocal of 1.8, the reciprocal of 1.8 is going to be 0.555. So we can have it as 0.5556, and this one is going to be hertz, the SI unit of frequency. Number 3, the speed of the waves if the student counted 4 ripples between the mass and NB of the tank. 4 ripples. So we can see that there is 800 meters. You can see that there is 800 meters. So we can tell ourselves that speed V is usually given by the distance over time taken. Therefore, a distance of 800 is covered within a distance of 800 is covered within 20, and so this is going to be 400 meters per second. Was that meters really? No, centimeters per second. Centimeters per second, or 4 meters per second if we convert the centimeters. State any 2 factors that would increase the speed of sound in air. Specifically increase. We are talking about specifically increase. So if we are stating any two factors that would increase the speed of sound in air. You know, generally there are factors affecting the speed of sound, but now we are categorically talking about increasing the speed. So to increase the speed, we need an increased temperature, increased humidity, increase in temperature of the air. We also need increased humidity, increase in the humidity, increase in the humidity of the air. Another factor which would increase is when the direction of the wind in the given location is in the same direction to the direction of the sound. So if speed, or if the sound wave is moving to the same direction as what? Same direction as the direction of the wind in the given area, then that sound is going to move at a faster speed. Greetings from Kericho. Thank you so much. Thank you. Okay, thank you for the correction. When you, yeah, it should be 4. It should be 4. I think I'm correct. This is good. This is good. Matungulu boys, thank you so much. Mr. Juma, you are getting your greetings from your students. This is great. This is great. Let's continue learning and sending greetings and love to our good physics teachers. Let's look at part C. An echo sounder of a ship received the reflected waves from a seabed after 0.20 seconds. Then we are told to determine the depth of the seabed if the velocity of sound in water is 1,450 meters per second. Determine the depth. In other words, we are determining the distance. We usually say that a distance is given by generally speed times time. But for this case, you discover that because of the reflection of the sound, this is an echo that we are receiving. The time recorded here is time for the sound to go to the seabed and come back to be received as an echo. And so we can divide the time by 2. So it's speed multiplied by half the time, so that we get time for one journey. So distance is going to be a speed of 1450 multiplied by half the time, 0.2, multiply by half the time. Or if we don't multiply by half the time, we can get the distance, but we say that such a distance is distance for 2 journeys, the sound to go and come back. So we divide the distance by 2. If you don't divide the time by 2, then the distance that you get will be for 2 journeys. You will have to divide it by 2. 1450 by 0.5 multiplied by 0.2, this gives 145 meters. 145 meters. That will be the distance. Remember to subscribe. Remember to share with a friend. Remember that our number for consultation is attached on the screen. This number, you can use it to request for revision materials. You can use the same number to appreciate the good work which we are doing in Shifting Grades Online School. When the ship above passes over a sunken reef, the echo sounder receives an echo after 0.16 seconds, determining the height of the sunken reef. So the sunken reef is again going to give us a height, whereby we need to take again speed. We need to take again speed, which is 1450. I hope I've copied it well. 1450, yeah. 1450 times half the time taken to go to the sunken reef and back. So we are using half the time for the reason. So 1450 multiplied by 0.5 or a half times 0.16. This is giving us 116 meters. That is the height. Let's look at number 12, a different topic now, from 4 for this matter. The diagram below shows an X-ray tube drawn by a student. Use it to answer the questions which follow. So we have an X-ray tube here drawn by a student. We have heating, we have point R, point S. We have a space there which is evacuated. We have P. Part 1, state with reason the material used for the part labeled R. Material used for the part labeled R. So for the part labeled R, this is okay, mostly this is the cathode. It's good for students to know that this is the cathode. We call it the focusing cathode. So the focusing cathode is made of a material of low work function. A material of low work function, so that when heating happens, it doesn't take too long to cause the muonic emission. And so we use metal oxides like barium oxide, strontium, a material of low work function. A material of low work function. Therefore, it must be a material of low work function to ensure that slight heating causes the muonic emission. Why is the tube evacuated? The tube is supposed to be evacuated so that when the electrons are emitted from the cathode, as they get accelerated toward the target by the anode, they don't lose part of their energy as they interact with air particles or particles along their path, to ensure that, to maximize, I can say to maximize the energy, to maximize the energy content of the electrons or electron beam. Energy content of the electron beam, since it does not interact. It does not interact with particles along the path. With particles along the path. Particles along the path. If it does so, it will cause ionization and lose a lot of energy. So the electron beam has to go with maximum energy. Remember, the greater the energy the beam has, the greater the energy also, which will be replicated in the X-ray beam being produced, and the more reliable the radiation is going to be. How can the wavelength of the X-rays emitted from this tube be reduced? It's good to know that there is a relationship between energy of the X-rays and the wavelength, and also the frequency. In other words, we usually say that energy equals to HF, Planck's constant, times the frequency of the radiation, which is also equal to, instead of frequency, we can have H and C over the wavelength. So we want to decrease wavelength. Remember, wavelength is inversely proportional to frequency. So when we are talking of reducing frequency, reducing wavelength, it means increasing frequency. And to increase frequency means to increase the energy content. So when the energy content is increased, then it means there is something which has to be accountable for that. And this is going to be increasing the potential difference between the anode and the cathode. Increasing the potential difference, increasing the potential difference, increasing the potential difference between the anode, the copper anode, and the cathode. Between the copper anode and the cathode. When you increase the potential difference there will be a great acceleration of the electrons from the cathode towards the target by the anode. When there is a great acceleration, then it means these electrons will be having very high energy, and also the X-rays produced will also have a great energy content, which means a great frequency and hence a small and hence a reduced wavelength. A reduced wavelength. You must be very keen in the explanation that I am giving. I can see people saying that they are from America. Wonderful. Yeah, barium oxide, wonderful. To prevent ionization, which in turn prevents loss of energy. You must understand that. Wow, this is wonderful. This is wonderful. People are also contributing. Moi Naikara boys in Narok. That is wonderful. Say hi to the physics teacher. Send greetings and love to your physics teacher tonight. Let them know that you are studying physics. Let them know that you are following up with Shifting Grades Online School. All right, we continue. We continue. X-rays are emitted when a tube operates at 3 times 10 power 2 volts and a current of 0.1 A, 0.01 amperes is passing through it. Take electron volt as 1.6 times 10 power negative 9 coulombs, and also mass of an electron as 9 times 10 power negative 31 kilogram. Calculate the velocity of the electron on hitting the target. So if we are accelerating electrons now using a potential difference of 3, then we are supposed to tell ourselves that the energy EV is also equal to the kinetic energy. The total energy which is required to make an electron move is also the energy which will be possessed by such an electron. And the energy which will be possessed by such an electron, remember the energy required to move through such a potential difference is given by electron charge multiplied by the potential difference between the two ends where the electrons are moving through. But now that energy will also be equal to the kinetic energy which the electron is going to possess. Kinetic energy is given by half m e v squared. Me is mass of an electron. V is the maximum speed that the electrons will move with. So we will say 1.6 times 10 power negative 19, multiplied by 300. This is the same as half mass of an electron 9 times 10 power negative 31 multiplied by the unknown v squared. Now we can play along with these values so that we get the value of v. So 1.6 multiplied by 10 power negative 19 multiplied by 300. Then we divide this by, or we can multiply by 2 first, both sides. Then we divide by 9 multiplied by 10 raised to power negative 31. Then with this now we can take square roots because v squared equals to 1.067 multiplied by 10 power 14, which means to remain with V, we need to obtain square root now. And so we get 1.033 times 10 raised to power. We have 1, 2, 3, 4, 5, 6, 7. 10 power 7 meters per second. This will be the speed of an electron. Please remember to utilize your calculator well and to confirm some of the figures which we are presenting here tonight. This is great. This is great. I can see we are still holding on. We are still holding on to the lesson. We shall continue. We shall continue. Remember, we are finishing up with the topic, with the whole paper, that is the minimum wavelength of the X-rays emitted. So now we are going to tell ourselves that the same energy, which is the EV, can also be given by H times C out of, instead of F, we are using C divided by the minimum wavelength. So we can make wavelength the subject of this formula actually. So wavelength equals to, when we take HC and we divide by EV. This means we can take Planck's constant. The theoretical value is 6.64 or 6.63 times 10 power negative 34. This one can be divided by multiplied by C. 3 times 10 power 8, that is the speed of light in vacuum, divided by EV, which is 1.6 times 10 power negative 19 multiplied by 300. And so we can get our minimum wavelength now. 6.63 times 10 power negative 34 multiplied by 3 times 10 power 8 divided by 1.6 times 10 power negative 19, and we also divide by 300. So we're going to get 4.14. 4.14 multiplied by 10 power negative 9 meters, because this is wavelength. So that is how you're going to get, that's how you're going to get the wavelength. Remember to confirm these values using your calculator. Say hi to your math teacher. State one property of X-rays. State one property of X-rays. X-rays can penetrate matter. X-rays travel in a straight line. X-rays have many properties. Kindly refer to your notes. They can be used to, they can be used in industries, in the medical field. They can be used in medicine to do what? To check cracks in bones. To also check flaws in metals. They are applied both in the industries and also in the medical field, among other properties, among other uses, that is. We can have number 13, which is on radioactivity, a very sensitive topic in Form 4 physics. We are going to discuss that. Say hi to your teacher. Moi boys. Kaplamai. Wow. Fractures in bones. That is wonderful. You can state as many as you know them. This is great. This is a great deal. You guys are really following up with physics, and I like that. I like that. I like this. I can see people are still interacting, but remember we are here for physics. Differentiate between a nuclear fusion and nuclear fission. Fusion is whereby two light nuclides merge to form one heavier nuclide with release of electrons. Two light or light nuclei fuse or merge to form one heavy nuclide with release of energy, while fission or nuclear fission is the splitting. Actually, the spontaneous should be spontaneous splitting. Spontaneous splitting of a heavy nuclide. A heavy nuclide to form lighter nuclei. Lighter nuclei with release of energy. Again, with release of energy. In both processes, a lot of energy is released. A lot of energy is released. Part B, the equation below represents a nuclear reaction. We have okay, this might be polonium or palladium or whatever it is, PO, undergoing some nuclear reaction to become A. Then we can see plus a radiation which has been released. Let's now look at the questions. Determine the values of P and Q. You should be told this, that the mass number before the reaction is also supposed to be equal to the same, or it should be equal to the mass number after reaction. So if we are seeing a mass number of 218, then on the right hand side of the equation, we are also supposed to see a total of 218. So because 218 is already at A, then Q is having a value of 0. We go to P, whereby there is an atomic number. If the atomic number is 84, then it means on the other side, we should also see a total of 84. This is already 85. That means the other one is a -1. So that when you add -1 and 85, we get back to our 84. That technique must be understood. This means if we are supposed now to write the particle which has been lost here, Y, then it would be having 0 and -1 at this point. With 0 and -1, it means this is an electron or simply a beta particle. Electrons are called beta particles. It's a beta particle released during radioactivity. You can see greetings here from a Jaden Goto Boys, following a guy who believes in physics. Okay, a guy who believes in physics. Greetings you, sir. Greetings to you, sir. You built my foundation. I receive your greetings, Jaden Mwendwa from Goto Boys. It is true that we started in Form 1 together up to Form 4. I must mention that. So thank you so much for following. Continue inviting friends. Let's look at Part C now. Let's look at Part C here. The figure below represents deflection of various radiations from a radioactive source S placed in a electrical or electric field between two plates, X and Y. The electric plate X is negatively charged. The other one, Y, is positively charged, as you can see. Identify the radiations marked with letters M and P. M, you can see it is being attracted or being deviated or being deflected towards the negatively charged plate. If it's going to the negatively charged plate, then it must be itself positively charged, and that must be alpha. It's an alpha particle. Now, if that one is the alpha particle, the other one, we can see it is attracted to the positively charged terminal. So it is actually what we've just discussed here. It's a beta particle. It's a beta particle. A beta particle. Now, the alpha and beta particle, without considering the sign of the plates where they have been attracted, we can also differentiate them otherwise by saying we can see the radiation P is greatly deflected, which means it has little mass. With little mass, it faces a greater deflection. So the radiation which has little mass is usually the beta particles, which is just electrons. Then we have M, which is not much deflected because of the great mass that it has. And so the heavier particle is usually the alpha particles, which face a slightly lower deflection. We can look at part D. Good work, teacher. St. Patrick's High. Wonderful. A sample of radioactive substance initially as 8 times 10 power 25 particles. The half-life of the sample is 98 seconds. Determine the number of particles that will have decayed after 294 seconds. We should know that remaining number is usually given by original number multiplied by half raised to power T capital out of T small letter. T is the time taken for radioactive decay to take place. Small letter t is the half-life. In other words, we can also write this formula this way. Then we have half raised to small letter n. Small letter n is given by number equals to number of half-lives. So we will be able to say that if the half-life of this sample is 98, then how many half-lives are there within 294? 294 over 98 becomes 3. So we will say that the remaining is equal to original number 8 times 10 power 25 multiplied by half, and half has been raised to 3, the number of half-lives. So this is going to be, when we take 8 and we multiply by 1 over 8, then we shall get 1.0 times 10 power 25 particles. But now we should get back to the question and we read it closely. The question says, determine the number of particles that will have decayed after 294 seconds. If we are getting the number that will have decayed, then we should know that this is the number remaining. We were calculating the number remaining. Now we go to the question and discover that we have to take 8.0 times 10 power 25 and we subtract the remaining number. This will give us 7.0 times 10 power 25 particles. This is what has decayed. This is the number which will have decayed. That is the number that will have decayed. I believe, you can see guys from Mark B. This is wonderful. Remember to say hi. Remember to say hi to your physics teacher. Remember to appreciate your physics teacher. Madam Wambua from Mark B. Madam Wambua is receiving her greetings tonight. This is great. This is great. Thank you guys from Machakos. Thank you guys from all over Kenya. Good work, mister. I like this. Remember, our consultation line is on the screen. That is the line that you're supposed to use for consultations, to ask for revision materials, and also the same line can be used to appreciate the work done in this platform. Somebody is mentioning something, but I encourage them to follow what I'm teaching and also to revisit your notes. I think the alpha and beta particles should be the other way around. No, it should not be the other way around. It is what I have discussed here. Thank you. State Ohm's law. Now, Ohm's law on electricity. Chavakali, thank you. Ohm's law, current electricity too. We are supposed to know that Ohm's law says that the current through a conductor or flowing through a conductor is directly proportional. It's directly proportional to the potential difference across its ends. Across its ends, the ends of the conductor, provided temperature and other physical conditions are kept constant. Other physical conditions are kept constant. That's how we state the Ohm's law. That's how we put down the Ohm's law. Then we are told that the figure below shows a circuit that can be used to verify Ohm's law, to show that voltage is directly proportional to current. We just want to show this. We introduce now a constant R. We want to show this. So we say that you can adjust vary current using a setup apparatus as shown, of course, then vary current using the rheostat. Rheostat is one of the variable resistors which are available in our laboratories. We can also use a potentiometer in the same place. So we are saying arrange apparatus as shown, then vary current using the rheostat. Vary current using the rheostat. Then after that, you can now record several values. Record several values of current with the corresponding values of voltage. Voltage is being made or being read from the voltmeter that you can see, current from the ammeter, which you can see here. It's like now we are tabulating, we are making a table, a value of current and the corresponding value of voltage. Now graph or plot voltage against current, and you say a straight line graph shows that voltage directly proportional to current, hence the Ohm's law is verified. Hence the Ohm's law is verified. So that's a simple procedure which you can follow to verify the Ohm's law. The graph below was obtained from experiment to determine the effective resistance of two resistors connected in parallel. So two resistors in parallel, then the value of one resistor is 50 ohms. The value of one resistor, 50 ohms. Then you are told this. We have a graph here. You can see current against voltage. From the graph, determine the effective resistance and also determine the value of the other resistor. The value of the other resistor. What we are supposed to know here is that the graph is of current against voltage. But now you should remember carefully that when we have a graph of voltage against current, we still get the same shape of a graph. We get a straight line through the origin. In this case, the slope gives us resistance. But now in this other case, whereby the axes have been inverted, then it means that the slope from this case now is going to give us 1 out of resistance. We are supposed to know that. In this case now, the axes have been inverted, and so the slope will not give us resistance. Instead, it's going to give us the reciprocal of resistance. This is from V equals to IR. Remember, this is plotted on the X, this one on the Y. Therefore, because this one is the X, its coefficient is usually the slope. The coefficient of the quantity on the X-axis will give us slope. But now, in this case, we have inverted the quantities. We have changed the quantities. So let's get the slope. We can get any two values, like a coordinate at this point, whereby I'm having a 5, 0.4. I'm also having another coordinate, like 2, 0.1. 2, 0.1. So now we can get slope by taking change in x, change in y, sorry, over change in x. So the first y is 0.4, the second y is 0.1. Then we can also take 5 minus 2. This is going to be 0.3 divided by 3. This is going to be 0.1. So if the slope is 0.1, then resistance, effective resistance, is going to be the reciprocal of the slope. And the reciprocal of the slope is going to be 10 ohms. So the resistance is going to be 10 ohms, the effective resistance. This one requires a serious analysis. A student must be very keen with all the attention in the paper. How can I get... I think somebody is answering you on my behalf, and that is good. Yeah. Dim the number below every page. Thank you so much. No, I'm not selling the papers. Somebody is saying, Nunua, I'm not selling the papers. Just get them for free. Thank you so much. Thank you, thank you, thank you. Wow. Let's continue. The value of the other resistor. Remember now what you've gotten is effective resistance. And now there is another resistor. There is another resistor such that the first resistor is 50 ohms according to the instructions here. That's why you are supposed to read everything. 50 ohms. So we are supposed to tell ourselves that now that they were connected in parallel, the instructions are saying they were connected in parallel. Now that they were in parallel, then it means 1 out of the resistance total is equal to the first resistor, reciprocal, plus the second resistor, reciprocal. So 1 out of 10 is equivalent to 1 over 50 plus 1 out of their known other resistor. 1 out of their known other resistance, it means we need 1 over 10 minus 1 over 50. And this is going to give us 0.08. Therefore, for us to get the second resistor, we need to take the reciprocal of this, which is 12.5. Because it's resistance, we write ohms. Being resistance, we write it as ohms. Okay, we continue. We continue. Thank you. People are liking. People are still subscribing. People are still sharing. Make sure all your friends will turn up tomorrow for a mathematics lesson. Please ensure that they turn up. Ensure that they turn up. An object O stands on the principal axis of a concave mirror as shown in the figure 9 below. By drawing suitable rays, show the position of the image. So for us to show the position of the image, we need to draw some suitable rays. Mark the word suitable. We are supposed to know that for a concave mirror, if a ray is close and parallel to the principal axis, it shall be reflected through F, through the principal focus. So we draw a ray. We draw a ray like that. This ray, it's going to be reflected through F. It's going to be reflected through F. Sorry, let me do it well. It's supposed to go through F. Remember, you can draw even 3 rays, but 2 are usually enough. 2 are usually enough. So that's how the ray behaves once it hits the mirror. There is another ray, which is through C. If a ray goes through C, the center of curvature, that ray should be reflected through the same path. So if a ray goes to the mirror through C, it goes back through the same path. And so it means in front of the mirror, the rays are diverging the more, which means they have a likelihood of intersecting somewhere behind the mirror. And so we can prolong. Remember, behind the mirror, now we use virtual rays, whereby we use dotted lines now behind the mirror. We use dotted lines. We also do for the other one. We do for the other one. We do for the other one. Yeah. Now the intersection of these rays is giving us the tip of the image. So the tip of the image is here. We can draw our image, also virtual. So we use dotted lines and we put an arrow at that point. Put an arrow. So this is going to be our image now, which is magnified, virtual, behind the mirror. Yeah, such things. And upright. It's also upright. Continue following. The difference between a convex and concave mirror, just follow the carving, the way they have been carved. You can even look at the top there, the slight carving. If the reflecting surface is bulging inwards, that is a concave mirror. If the reflecting surface is bulging outwards like this, then it would have been convex. It would have been convex. So this one is a concave now. Determine the magnification. So magnification can be given by height of image divided by height of object. The same can also be given by distance of the image. Distance of the image can be given as small letter v divided by distance of object, small letter u. Small letter u. So you can work out that, please. In case you get this paper, make sure you print it and you construct so that you may measure the distances according to what you get in the paper. Okay, in an experiment to determine the focal length of a converging lens, a group of Form 4 students collected some data and used the results to plot the graph shown in figure below. So this is a graph whereby Form 4 students have plotted magnification M against image distance V in centimeters. Using the graph above, determine part 1, the object position when the image position is 45. So we start by identifying image position of 45. Then we move along that now. Image position of 45 should be between 40 and 50. That is the point. Then we read the magnification now. When you read the magnification, we read the magnification there. The magnification is 3.5. So if the magnification is 3.5, then we will tell ourselves that magnification is given by image distance out of object distance. So 3.5 magnification is given by, we are determining position of image. Determine the object position when image position is 45. So 45 is known image out of unknown u. So the value of u is going to be given by 45 divided by 3.5. This will be 12.86. 12.86 centimeters. Yeah, that is it. Remember, we are winding up. Remember, we are winding up with this program. Remember to subscribe. Remember to share the link with friends. Remember to be around tomorrow for a physics discussion, for a mathematics paper 2 discussion. It's going to be very beautiful. Invite a friend. Tomorrow, don't be alone. Those who don't take physics, tell them that mathematics is compulsory and we shall be meeting online. Slope of the graph. Let's look for the slope. Definitely we need change in y over change in x, and we must identify a few coordinates. Coordinates like 45 and 3.5, we are already having that. Coordinates like 45, 3.5. Can pick more coordinates. More coordinates like, can pick another coordinate like 30 and 2. 30 and 2. So we just pick coordinates and we show them. And pick that coordinates so that you may show the change. So this will be the change in the x. This will be the change in the y. So now we have 30 and 2. A coordinate of 32. 32. So now for us to get slope, remember we are winding up and I can see people are really increasing. Say hi to your physics teacher. Please send greetings to your physics teachers. We are having a now change in y, 3.5 minus 2 divided by 45 minus 30. This is going to be 1.5 divided by 15. Are you getting 0.1 like me? The slope is 0.1. We can give it some units. Remember, this is magnification, no units, but image distance on the y-axis, on the x-axis, is having some units in centimeters. So this is going to be divided by centimeters, or we say per centimeter. Per centimeter. The question here is saying we determine now the focal length of the lens, given that m, that is magnification, equals to v, image distance out of f minus 1. So we are supposed to know that graphs can be analyzed following the general equation of straight lines, whereby we say if this one is on the y-axis, that is m, then it is v, which is on the x-axis. That means the coefficient of v is 1 over f. That's why we have v here, minus 1. So this is on the x-axis. This one is on the y-axis. This is now our constant c. So we will talk about the constant c, that is the vertical intercept for this graph, is supposed to be -1. So such a graph should cut through -1 automatically, because that is our y-intercept. Then something again that we are supposed to know is that the slope of the graph, the slope of the graph is supposed to represent 1 over f, which means for us to get f now, then we need the reciprocal of the slope. So the reciprocal of 0.1 is going to exactly be 10 centimeters. This remains our consultation line 0704 153 366. Request for papers, consult us, and also use the same line to appreciate the good work done in shifting grades. Thank you so much for being patient. See you tomorrow for mathematics. Good night.